Hello there and welcome to sections 12.7 and 12.8. In these sections we're going to build on our discussion of vector functions from the last two sections. And so to kick things off, let's check out the first question on the worksheet. It says, consider the following trajectories of two bugs moving in the plane. So for little r of t, it's 2 cosine t comma 2 sine t, and t is greater than or equal to 0. And capital R of t, that's 2 sine 2t comma 2 cosine 2t, and again t is greater than or equal to 0. Now part A says to describe the paths that each bug move along. Okay, so looking at little r of t, okay, notice that we have parametric equations for the circle of radius 2 centered at the origin. Okay, and the reason why is that if we look at x squared plus y squared, well, that's 4 from the Pythagorean identity, right? And this equation, x squared plus y squared equals 4, is a Cartesian equation for this circle. Right, now furthermore, since x is a cosine function and y is a sine function, when t is 0, the bug is located right here at the point 2, 0. And since x is a cosine function, as I let t increase a little bit past 0, x will decrease, meaning the bug is moving to the left of its starting point, and y, being a sine function, will increase, meaning the bug is moving up from its starting point. So this is a counterclockwise parameterization of this circle, okay? And also note that since the period of these sine and cosine waves is 2 pi, okay, the bug will complete a trip around this circle in 2 pi units. All right, now for capital R of t, we again have a parameterization of the circle of radius 2 centered at the origin. Okay, if I look at x squared plus y squared, well, that's 4 from the Pythagorean identity. But now x is a sine function and y is a cosine function. So when t is 0, we note that the bug is going to be located at the top of the circle at the point 0, 2. And since x is a sine function, if I let t increase a little bit past 0, x will increase, so the bug is going to move to the right of its starting point, and y, being a cosine function, will decrease, so the bug is moving down from its starting point. So this is a clockwise parameterization of the circle. Okay, and furthermore, right now the arguments of these sine and cosine waves is 2t as opposed to just t, right? So their periods, right, are just now pi. So this bug will complete a trip around this circle in pi units as opposed to 2 pi units. So we just note that the second bug, in fact, has double the speed as the first bug. All right, cool. So now let's check out part B. It says, compute the velocity and acceleration vectors for each bug at any time t is greater than or equal to 0. Okay, well, as we saw in the last two sections, the velocity by definition is the rate of change of our position vector with respect to time. So in other words, it's just r prime of t. And to compute the derivative vector, we just differentiate component-wise. Okay, so this will be negative 2 sine t comma 2 cosine t for the velocity vector of little r of t. Okay, and I make a note here that says that if I take the dot product of our position vector little r and our velocity vector v, I get 0 for all t. All right, so let's check that. The product of the I components, that's negative 4 cosine sine, and the product of the j components, that's positive 4 sine cosine. And when you combine those products for the dot product, you're going to get cancellation, and you get 0, right? And that's true for all t. So that implies that this green position vector and this orange velocity vector are in fact orthogonal. Okay. Now in the last two sections, we saw that the velocity vector, so in other words, the derivative vector, always points in the tangential direction to our path in the direction of increasing t. So if we're located, say, at the tip of this green position vector right here in quadrant 1, okay, the direction of increasing t, well, is indicated by these yellow arrows, right? This is a counterclockwise parameterization. So the velocity vector here, right, points in this direction you see here, sort of this northwesternly direction. Okay, now also note that since we are moving along a circle, okay, there is a fact from geometry that says that if you look at a tangent to a circle, okay, that tangent will be perpendicular to the radial line, okay, that passes through the point of tangency. So that really is in agreement with what we're seeing here with the dot product. But okay, now let's go ahead and check out the velocity vector for capital R of t. Okay, so again, we differentiate component-wise, and we're going to pick up, right, a factor of 2 from the chain rule. So we get 4 cosine 2t comma negative 4 sine 2t. Okay, so here, notice again the dot product is always 0, so the product of the I components is 8 sine cosine. The product of the j components is negative 8 cosine sine, and again we get that cancellation. So the position vector in blue and this velocity vector in orange are orthogonal, right? And since we know that the velocity vector points in the direction of increasing t, right, since this is a clockwise parameterization, if I'm located right here in quadrant 1, the velocity vector will point in this direction here, right, this southeasterly direction. Okay, so the other thing to point out here, since we're picking up this factor of 2 from the chain rule, okay, that is going to affect the length of the velocity vector. So if you look back up at the velocity vector for little r of t, right, this magnitude is actually the same as the magnitude of r of t, right? If I take the square root of the sum of the squares, it turns out I'm just going to get 2, right, from the Pythagorean identity, and that's exactly the magnitude of our position vector. We're not picking up a factor of 2 from differentiation, right? Here we are, though, for for capital R of t. So that implies that the velocity vector, in fact, will be twice the length of our position vector. Okay. Let's check out now the acceleration vector. So we're just going to differentiate again, right? So a of t, that's going to be negative 2 cosine t comma negative 2 sine t. Okay, that's for our first bug there. And notice here that this is simply the opposite of our position vector, right? The I and the j components are the same as what you see for the position vector, except there's just these negatives in front. So I note here that the acceleration vector is simply the negative of our position vector. So that implies that the acceleration vector will always point directly towards the center of this circle, okay? And in this case, okay, the magnitude of the acceleration is actually equal to the magnitude of the position vector. Okay, so now for capital R of t, okay, differentiate twice, and you get negative 8 sine 2t and negative 8 cosine 2t. So we pick up this factor of 2 once again, right? So here, right, now we have that the acceleration vector a of t is negative 4 times capital R of t, right? It's negative 4 times our position vector. Because notice for our position vector, the coefficients are 2, and now the coefficients for the acceleration vector are negative 8. Okay, so that says, well, once again, the acceleration vector is going to point in the direction directly towards the center of the circle, okay, but now, right, from these factors of 2 that we keep picking up from differentiation, okay, that's going to stretch that acceleration vector out. It's going to be actually 4 times as long as our position vector. Great. All right, and then last up is part C. It says compute the speeds of each bug. Okay, so the speed by definition is the magnitude of the velocity. So for little r of t, computing its speed, I want to take the square root of the sum of the squares of the components of the velocity vector. So that's negative 2 sine t squared plus 2 cosine t squared under a square root. From the Pythagorean identity, right, that simplifies to 4 under a square root, so that's equal to 2. And so notice here, the bug is moving with constant speed, okay, as it moves around this circle, and that constant speed is 2. Okay, now for capital R of t, right, bug number 2, do the same thing. We look at the square root of the sum of the squares of the components of its velocity vector, so 4 cosine 2t squared plus negative 4 sine 2t squared. From the Pythagorean identity here, this is going to be 16 under a square root, so that simplifies to 4. And we note here, right, that Well, this bug also moves with constant speed, and this bug's speed is twice the speed of this first bug. Okay, great. Well, that does it for this question, and I will see you in the next video. Thanks so much.